Welcome. This DDI CADcast will cover connecting the design dots. I'm Enrique Garcia. So when a designer is tasked to create a brand new product, with any design there are many drivers or many different aspects of the model or the design that we have to take into account. Now the goal for this presentation is to show you how quickly and easily we can take many of these different drivers, combine them with our initial design to create a more effective, efficient, and higher quality product with significantly less time in the design process. So traditionally, a typical design process starts out with your initial design. You're looking at all aspects of your geometry. Now within the past 10 years, we've started to take into account sustainability or the structural results or strengths of our models and weight into account of this. The benefit behind that is that it reduces our overall weight, can save us tremendous costs, and allow for greater design insight at the very beginning of our workflow with this model. Now later in the process, we may go back and redesign our models for decreasing costs and looking at the marketability of our product. Then even further down the line, we may go back and look at the environmental impact of our product and the maintainability. Now, towards the end of this process, we've lost tremendous amount of time and used much resources to drill down to the best configuration of our product that takes into account all of these different aspects in our design process. Also, how much time does it really take to go back through this process and look at new ideas to reevaluate your strength, your marketability through this process to go and amend your initial design? So this typical design process renders itself to be greatly inefficient. So let's take a look at perhaps a better design process. A method that we propose at SolidWorks is to take all of these different design drivers that may have been necessary to occur later on during the design process and plug them all up front. If we do this as a front-loading process where we take our strength, weight, cost, and environmental concerns up front, we're going to have not so many what we call downstreamers, reducing cost and overhead when it comes to going back and making design changes. So using the capabilities of SolidWorks, let's go ahead and go through a workflow so we can examine the strength of our model using SolidWorks simulation. Then we can look at cost of the model, looking at different versions of our parts, and determine which material will yield the best cost estimate. Then let's take a look using SolidWorks sustainability, the environmental impacts each different revision will make to our environment. So let's take a look at material. So which is our go-to material typically? It's usually going to be our 304 stainless steel when we're not sure where to start out with. So luckily we can use SolidWorks simulation to help us make this decision. So let's jump into SolidWorks and let's explore our design with regards to material and gauge size to see what kind of trends we get with our structural results with our part. So let's start out with our simple SolidWorks sheet metal part. It's composed of AISI 304 stainless steel material with a gauge size of, it's a 14 gauge size thickness. Now let's assume we do a crush test with all of our different parts. So let's use SolidWorks simulation and set up a structural analysis that will have 50 pounds force pushing down along the X direction, essentially simulating a crush on this stainless steel part. Let's go ahead and run the analysis, and let's look at some results. So let's look at our maximum stress, which we can tell here that we're a little bit over 2000 psi. If we do an animation of our results, we can see where we are getting the most stresses in our results. You can tell here that this is an exaggeration of our true scale. We're about 200 times exaggerated here to give you some qualitative information as far as where our major stresses are being applied. We can do the same thing when it comes to our displacements, and also an even more insightful result could be our factor of safety. If we examine our factor of safety, we can see that our minimum factor of safety is going to be 12.95, which essentially is saying that we can apply essentially almost 13 times the amount of loading that we have in this model before we get some failure in our part. Now let's take our design and increase the thickness of our sheet metal part. Let's go in and increase our gauge to maybe a 10 gauge size, and let's rerun our crush test. We can see by changing the gauge size that our factor of safety, or our minimum factor of safety, went down to 5.8. Now let's go ahead and change our material type. Let's see what happens when we apply a plain carbon steel material to our model with regards to our structural analysis. We can see as we apply the plain carbon steel, our minimum factor of safety has increased to 6.3. So we could either take this and continue to manually apply different constraints to the model and get some comparative results based off of one or the other, or you could determine some trends by using design studies. Design studies is a method that allows us to apply some variables. In this case, we can look at the different gauge sizes, and then we can get some results under constraints. We can look at displacements, stresses, or also in our case, we can look at factor of safety results. When using design studies, we can get trends, such as what you see here in my next slide. Now let's take a look there. We've gone in and we've analyzed our 304 stainless, and looking at factor of safety, we can see that if we're going to use a factor of safety of 3 as a pass or failure transition line, then we probably want to be around maybe a 14 gauge either stainless steel or galvanized steel or plain carbon steel. Now if we want to use aluminum, we would probably have to go down to maybe about 9 or 10 gauge aluminum to satisfy our structural requirements and our strength values for this design. So with SolidWorks simulation, we were able to determine which gauge size and which material seemed to be the best combination as far as getting the maximum performance out of our parts. This greatly helps us with regards to over-designing our models, but also when it comes to over-designing, this could also mean cost. So with SolidWorks costing, we're going to calculate what each feature on this particular sheet metal part costs and use that estimate to evaluate the material and geometry options and the trade-offs. So we first start off by having a baseline cost of our part. Now when we look at SolidWorks costing, we have different templates such that we can go in and use different units. In this case, we're going to choose just English Standard, and we're going to be looking at our typical 304 stainless steel. And let's choose something with a thicker size, maybe a 10 gauge thickness, and let's use that as our template or our starting baseline point. The software is going to go in and analyze our parts and give us a nice little report to the left-hand side showing us what a standard setup and cost setup would be. Also, it'll go through and look at each individual aspect of our cuts and give us a dollar value for each individual laser cut that gets calculated with SolidWorks costing. Next, it's going to go in and look at different bends that may be required to generate the part and give us an associated cost with that. Lastly, if you had anything extra that needed to be taken into account, I can go in and add any custom operation and tag a certain setup and operation cost to associate that with that feature. And if you had certain bends that perhaps you want to discount or not include in the costing, we could also apply a cost, no cost option in there, and that will go in and remove that price from our baseline. So now that we have a stainless steel material for this, we have a costing of a proposed costing of $164. Let's see what happens when we change our gauge size. We choose a different gauge size. let's choose 14 gauge size. Now we should see that we're using less material, hence our cost is going to be reduced by 42%. Let's try a different material perhaps for this. Let's use a gauge of 14, and let's switch this from stainless to galvanized steel. We have a greater reduction in cost there. We have an 86% reduction in initial cost if we go from stainless steel to galvanized steel, and we go from a gauge of 14 to a gauge, in this case, of 22. So again, changing these different parameters, we can kind of get a trend of what our cost is going to be in the end. Now, since we've spot checked a couple of different costing scenarios, let's look at our trend graphs. After doing some comparative analysis, we can see here that as far as cost is concerned, our plain carbon steel is going to give us the lowest possible cost with the same structural performance. We saw in SolidWorks simulation that we can still get a passing factor of safety with plain carbon steel, and here we can see that we can get the best cost using this material. On the other hand, if you want to step it up a notch and go with stainless steel, you're going to be paying a premium for the same type of structural results or same strength results you'd be getting with plain carbon steel. Now, if you're going to go with aluminum, you're definitely going to be a very, very lightweight, hence you have to increase the thickness, and we can use a 8 or a 9 gauge aluminum material, which is not so bad if you look at our cost. So currently we have results for two different aspects of our models. We have the costing results and trends. We also have our strength results and factor of safety trends as we've changed the material and we've changed the gauge thickness. Now let's take a look at environmental impact of this particular parts as we change different aspects of the design. For this, let's turn on SolidWorks Sustainability. And let's go ahead and set a baseline just like we did in costing. Let's set a baseline with our same stainless steel, our 304 steel material. Now, sustainability, we can go in and we can take material constraints into consideration. We can look at the manufacturing location, how many years is it built to last, the process of the manufacturing, location of usage, which will take into account transportation, resources, and also the end of life, how you're going to dispose of the material, whether it's going to be recycled, landfill, or incinerated. We can take all of these different parameters and do some comparative analysis. So we're going to leave the defaults using this exact geometry and gauge size with our stainless steel material, and then we can look at some trends. So again there, let's set our baseline, and now let's change our material here to maybe plain carbon steel. And just by changing our material, we can see that our carbon footprint has decreased by 50%, energy resource has greatly reduced, our sulfur dioxide amount has decreased by 50%, and our water consumption has greatly reduced there to 94 reduction rate. Also, our material financial impact has decreased by 75%. Let's see what happens when we change our material to an aluminum. Now when we change to our aluminum flavor of 6061, we can see that we're just at the cusp there of our stainless steel as far as environmental impact. We're still a little bit less comparatively speaking. So if we were to go between choosing aluminum or plain carbon steel as far as the environmental impact, definitely the best choice would be plain carbon steel. So just like simulation and costing, this SolidWorks Sustainability is a quick and powerful tool that will give me a simple estimate on the ecological impact of my design. So now we can easily compare the environmental impact from our 4 different design options. So again, we are going in and we're looking at phosphates in the water. We're looking at sulfur dioxide created in air. We're also looking at energy and manufacturing, disposal, and actual use of the model if it applies. And lastly, the carbon footprint of our of our design as far as carbon dioxide. Just from our quick analysis here, we can see that either our plain carbon steel or our galvanized steel is going to be the better choice when it comes to looking at the environmental impact. Also, by looking at our different results in SolidWorks sustainability, we can see where most of our environmental impact comes from. It looks like it's going to be our material at 88%. As far as our energy impact with SolidWorks sustainability, we can correlate this with our slide here as far as hours of watching television. Next, let's look at the carbon impact with sustainability. Again, if we were to compare plain carbon steel versus our baseline 304 stainless steel, we can see that there's a difference of 18 miles being driven per part if we were to correlate one part equals X amount of miles. So if we think of it this way, if I were to go in and run a batch of 1,000 parts, we're looking at 18,000 miles difference between our 1023 steel and our 304 stainless steel. That's a huge impact. That's like, that's like maybe driving from coast to coast, east coast to west coast 6 times. So again, we're looking at monumental differences when it comes to material selection. In a couple of minutes, we're able to improve our bottom line or change our baseline from using stainless steel to perhaps going with the plain carbon steel material, or you can start marketing your products towards a green consumer and ultimately design better and more environmentally conscious products. Here's a quick article from the Harvard Business Review indicating why sustainability is now the key driver of innovation. So let's take a look here, a grand overview when it comes to strength, weight, the manufacturing cost, and ecological benefits or metrics as we analyze these between the different types of materials that we're looking at with our SolidWorks products. So if we look at strength and using SolidWorks simulation, we can go in and modify our gauge size and our materials to satisfy our strength criteria. That's not a problem. And again, that's something that's been a nice trend and has been something that's been a common use within the past 10 years. Now we can look at weight. This is using just CAD and SolidWorks data. We can see that aluminum there is definitely the less dense, the more lightweight material amongst the four. Then we can look at costing using SolidWorks costing, and we can see there that our plain carbon steel and our galvanized steel yields us the better cost benefit as compared to our stainless steel and aluminum. And lastly, we can look at the ecological or environmental benefits when it comes to using our 4 materials. Now, had we been using our typical design process where we're looking at the strength and the structural results of our products with CAD, we would probably go in and look at our aluminum material and maybe have chosen that for our first rev. Then down the line, had we done, again, this typical design process, we would take a look again at the actual manufacturing costs and the environmental impacts, and then we probably would have settled with our plain carbon steel. Again, that would have been perhaps months or years down the line. If we go in and group all of these different drivers and look at them at the same time, we would start with our first revision, and now we can pick the best material looking across all 4 lines. And again, it's never too early to start considering these different drivers, since there's always a cost involved with changing your different revisions and employing all your different overhead resources. So in general, 80% of our product's cost and environmental impact is determined within the first 20% of the project cycle. So these tools give us a closer look into our designs and help us work in tune with our design drivers. And since we have this information up front, we can save time, money by reducing this amount of downstream work. Also, SolidWorks sustainability gives us this insight early on when our design space so we can make better, healthier changes with respect to our environment. And just the bottom line is that everyone has to make changes to their models between different reviews, so minimizing this definitely helps. So the more data is just better than less data, and this will make the design process more efficient along the way. And thank you for viewing this Digital Dimensions CADcast. please visit us at www.ddicad.com.